Okay, I thought we'd do some analog circuitry. Too much digital circuitry these days. But let's take a look at a simple one transistor circuit here. And this will be going to some VCC. It'll be 5 volts when we're breadboarding it up, but 5 volts in, and we have a transistor, and this is an emitter follower. So we've seen this before. Whatever you put here kind of ends up here, so it's a gain of 1 amplifier. And but if we take a look at this in DC conditions, we had a voltage drop across the diode, right? So this transistor looks like 2 diodes. It looks like one diode in this direction and a diode in this direction. And that's the way you can test these transistors also, is you can use a voltmeter and make sure these 2 diodes are still okay. And so what we want to do is we want to place a voltage here and then measure the voltage here and look at that voltage drop. So we can do that by maybe putting a couple resistors over here. We'll put a 10K and a 10K and a 1K. Okay, so here we should get some voltage that's halfway between ground and VCC, and then over here we should get a voltage that's a diode drop away from this voltage. So so let's do that. Okay, so here we have our transistor, and it's connected to VCC on its collector. And then there's a 1K resistor from emitter to ground. And then on the base, we have this circuit. The base, we have a 10K resistor to +5, and then a 10K resistor to ground. All right? So if we use a voltmeter here, let's see if we can't get it all in the picture here. Nice. Let's see. I think you can see that. All right, so let's measure the VCC. It's 4.9 volts. So if we measure the voltage here, that's the halfway point. We're measuring 2.396, so let's take 2.4. Let's see, so if we go to our circuit here, we have 2.396 here. And if we measure the output of the transistor, that 1K resistor, we have 1.748. Okay, so if we get our calculator, 2.396 minus 1.8, we have 0.648. Okay, so we have 0.648 volts across the transistor, and that's our diode drop, 0.6 volts. And so everything's working just fine here. So what is this circuit doing? Well, it's outputting a voltage. It's also creating a current through that resistor, right? So the current through that resistor is 1.748 volts divided by 1,000 ohms. We can do that, 1.748, 1,000. It's creating 1.7 milliamps. Okay, one thousandth of that, 1.748 milliamps. Okay. So, where is that current? Well, that current is through this, it's hard to write this thing. That current is through this resistor. It's also through this collector. It's got to come from somewhere. So it's coming from this and going through here. So there's, 1/100th or 1/300th because of the beta of the transistor current in here. So we're going to ignore the current into the base. We're just going to say this current here is also the current there. So we could put an LED here in the circuit. Let's put an LED right here. So if we put an LED right there, that LED should be lit up with 1.7 milliamps. Okay. So we'll disconnect the 5 volts here. We'll get an LED. And the LED will go in here like this. And there we go. So, oops. So the LED is lit up with 1.78 milliamps. Or 1.748 milliamps. So we have a current source. We've created a current source with one transistor. Now that current source is going to vary with the VCC because the voltage will go up and down, which means the beta, the half of that will go up and down, and the base voltage will go up and down, and then the voltage across that resistor will go up and down. So we want something a little more stable. Okay. Instead of using two transistors, we could do what we've seen before on our amplifiers where we use a diode. So let's take a look at that. Okay. Get another piece of paper. Okay, so what did we do before? We said we're going to have a we need to put a voltage here on here, and we know that we have to overcome one diode drop, and then we'll have another diode drop. So in this particular case, we're going to be putting about 1.2 volts here, or about 0.6 volts here, right, after the diode drop. So one of these diodes kind of accounts for the transistor over here, and then one of the diodes is acting as a voltage reference. Okay, we're kind of hoping these diodes don't vary much with temperature or other things. We're kind of using them as poor man's Zehners, right? We're just kind of trying to create a fixed voltage. But it will be pretty intolerant if we go from 5 volts to 6 volts. This voltage here won't vary much. It'll vary a little bit, but it won't vary as much as it normally would have. So let's build this circuit and see how it does. All right. So instead of that, we will put in one diode. Let's see here. These breadboards are sometimes a little hard to work with. Get them to go in. There's a diode. And here's another diode. I don't know if these are, the legs are long enough on these diodes to go all the way through. Hopefully it is. Let me use this. Try to poke them in. Make sure they're nice and nice and seated well. Oops. They are wanting to pop out. I probably should have used a diode with a little bit longer legs. And then we'll use a ground here. And so now hopefully we have our resistor, our two diodes. Sorry, my camera went out of focus there somewhere. But what I have now is this circuit. I have 10K to 5 volts. It goes through two diodes and then to ground. So we should get about 1.2 volts here at the second diode. So let's measure that. Zoom out so we can see everything. Okay. I'm going to measure the voltage here and turn on our power. And there we go. We've got 1.12 volts here. Okay. So let me write that down. 1.126. And then over here, we have 0.5 volts. 0.506. All right. So now we've got 1.1 volts here. We've got 0.5 volts here. We have a 1K resistor, so we have 0.5 milliamps. We have 500 microamps. All right, so 500 microamps. That 500 microamps has to go through the whole thing. So our LED is being lit up now with 500 microamps. Right? So a little bit dimmer than it was before, but we have 500 microamps. So let's say we want to duplicate the circuit, and we want to drive a bunch of LEDs all at the same current. Well, there's something called a current mirror. They're very popular inside ICs. You don't see them outside of ICs very often, but inside ICs you see them quite often. But they're still a handy circuit to have. They are actually better if you have matched transistors. So inside an IC, all the transistors are matched really well. But in general, transistors are okay. So let's see if we can't build a current mirror. Let me draw a diagram of that. So we have built a current source. So let's say we have a current source. A lot of times current sources are drawn like this. So we have some current source already. And let's say that we want to have multiple current sources, right? And what we're going to do is we're going to use PNP transistors this time. We're going to have a PNP. And we're going to connect that PNP to this current source. So we have current going through this transistor here. And we want to have another one because we want to have several of these. Let's put a couple more in here. So we really want to have three currents. We have 3 LEDs. We want to light 3 LEDs up all with the same current, okay? If we take the emitters of these, I mean, not the emitters, the bases of these transistors. I'm going to connect them all together so these 3 bases are all shorted together, right? And if I have an LED here, I have an LED here, and I have an LED here. Now these LEDs, I want to have the same amount of current going through all of them. If I take this base and I actually short it out to this collector, this thing will act like a current mirror, strangely enough. So whatever current goes through this will get mirrored. So this is already creating a current. We're creating 500 microamps. All right. Now, by connecting the base to the collector, that turns this transistor on no matter what. There's always a way for the electricity to flow, so it can go either way. And it will start to conduct, but it will only conduct up to 500 microamps because we have a constant current in this leg here. But that sets a condition in this transistor, and that condition is this 500 microamp condition. So it kind of sets the base voltage. And if we set the base voltage to these other transistors, and if these transistors all have the same characteristics, then the conditions of these two transistors will also be such that you'll get current in these two transistors, LEDs as well. And these three LEDs should light up to 500 microamps. So let's build that circuit. All right, so this is the circuit that we're going to breadboard. We're going to use our original circuit here. This is the two diodes, and we have about 0.5 volts here. So we have about 500 microamps flowing through here, which means we have 500 microamps flowing through here, which means we have 500 microamps going through the LED and through this resistor or transistor. And its base is tied to its collector, and it's also duplicated in these two. So if everything is working right, whatever current we have here will also be here, it will also be here, and these three LEDs will light up to be the same intensity, around 500 microamps. Okay, so sorry about that. Zoom in here. So here we go. We have this is our original transistor that creates the 500 microamps, and that comes over here to this LED. So this is in the same order here, right? So this is over a different place now, but these three transistors are these three transistors here. And if we turn it on, we have three LEDs lit, and we should have the same amount of current flowing in each one. Now that current's going to be a bit different depending on the characteristics of these three transistors, but let's go ahead and measure them and see how constant it is. All right, so let's see how good this thing is. Let's measure those three currents and see what kind of tolerance it has. So we can measure the current in this leg here. Let's see here, let's measure milliamps. And we can break the connection here. And we're getting 511 microamps. Okay. I can break this connection. We're getting 562. And break this connection, we're getting 530. All right. So let's get out the calculator. 512 or 511, 562, 530, 3 divided. Okay, so our average is 434. Sorry, 534 as our average. And 534, this one's going to be 20 minus 23. And this one's going to be plus 8, plus 18, plus 28, plus 28. and this one's going to be minus 4. Okay, so about plus minus 20, 25, something like that. Let's look at worst case here. 28 out of 560, out of 534. So 28, 534. So this is about minus 5%. Okay, so we're current mirroring to about absolute error of 5%. Some better, some worse. So yeah, not too bad. Doesn't use many transistors. Again, it would be much better if the transistors were matched. And it also is the simplest type of current mirror. There's other types of current mirrors. You can look up Wilson current mirror. It adds another transistor. It kind of adds it into a cascode place, I believe, and creates a little bit better voltage reference and tolerance, and doesn't vary as much. But yeah, we're looking at a pretty good current mirror. Very few components. Okay, so what else can we do with this? Well, if we take a look at this here, this is our current source, and if we say want to modulate these LEDs, what we could do is we could take this here over to a transistor, and we could basically short these guys out, and that would turn all the LEDs off. So if we added this transistor, let's say we put in a 1K resistor or something like that, we could actually use this circuit to pulse modulate our circuit up here. So let's put that in. All right, so I've added one more transistor. The collector of that transistor is here at the second diode. The emitter is grounded, and then the base has a 10K resistor. And we'll take that 10K resistor and we'll go up here to our clock circuit. Remember, this clock has a 555. This thing has a 555 in it, and there we go. So yeah. So now we can use one transistor to control all three resistors, all three LEDs. So it's a good way to minimize circuitry if you need to control lots of things equally. You're just mirroring whatever's happening over here. So pretty good.